So that's the topic, observational charge exchange challenges. First of all, many thanks for the invitation. It's really great to be here and to talk about the topic which I personally quite. Fascinating. Actually, I'm an observer, so I don't do experiments, I don't compute, I just observe. But still, there's enough to be done. And I thought, in the spirit of this workshop, it might be a good idea not to present final results, but to really to confront you with reality, with all the problems one is faced with when one wants to extract most of the X-ray signal which we get. I mainly focus on, I focus on comets, because I'll show in a moment that I think this is the most rewarding targets if we want to study the physics of charge exchange. And I will concentrate on XMM Newton. If you scan the literature, you won't find many publications. You will find a lot from Chandra, but not many from XMM Newton. This does not mean that this instrument is not suited. On the contrary, you are, as an observer, overwhelmed. In the case of Chandra, you have one CCD, essentially, ACIS S3. Here you have 5 X-ray instruments in total, plus an optical monitor, which can be used with different filters and prisms and all that. And it's quite some challenge to combine all this data in a consistent way. So I'll try to show you. Before I go into the problems, I'd like to highlight the importance of the comets so that you have a chance to survive the rest of the talk. And well, I think of comets, this is a very interesting experiment which nature does for us. Essentially, we have a huge cloud of neutral gas called cometary coma, which is irradiated by a beam of highly ionized ions called solar wind. And this laboratory has a size of millions of kilometers, and this is all done by nature itself. You just have to observe that. And also interesting is that there are no complications. There are no other competing emission mechanisms. They may be present, but so far no one has been found to be able to compete in any way with the charge exchange X-ray emission. So we have a very fortunate case. We have pure charge exchange X-ray emission, and in order to study this, we can utilize the full instrumental setup what we have. We have special spectral resolution, spatial resolution, and temporal resolution. This all can be utilized for comets. And one very wonderful property of charge exchange is this very high cross-section, and this is nicely illustrated in this comparison of an optical image. And now comes the X-ray image superimposed, and you see how much farther out you can trace the X-ray emission. This is an XMM Newton image. So this is, I've said this already, comets are very rewarding targets, and in short, I think they can be considered as benchmarking experiments for testing our understanding of the physics of charge exchange. So having said this, now let's go to the problems and challenges. The first one is quite obvious. Comets are moving and extended objects. And this already creates some deviations from the standard analysis techniques which are applied for analyzing typical X-ray sources. This is shown here. This is the field of view of XMM Newton. As I said, you have many instruments superimposed of each other. Here are all the instruments projected onto the sky. This is celestial coordinates, right ascension, declination. And this is a typical length of motion of a comet during such an observation. Obviously, we need to repoint the telescope several times. We have done this 6 times in this case of observation, and then let the comet pass through. The events are all time-tagged, so we can do all the transformations into the rest frame of the comet later on. And this is what the detector sees, the pure raw data. So repeatedly the comet moved along this diagonal line. And the first challenge, of course, is to clean this data set. And for this purpose, it's important to produce 2 types of maps, so-called exposure maps. This shows the sensitivity of the instrument projected onto the sky. It has vignetting. This is a general property of X-ray telescopes. The flux is higher in the center than at the edge. But there's also another type of map important. This is a flat map. This is for the background, because the detector itself also produces events, and they have first to be subtracted before one divides this by the exposure map. Otherwise, one would get an overcorrection at the edges. The real photons look like this. It's quite interesting. It's the same data set. The only difference is that here I've selected energies higher than 1 keV, here it's lower than 1 keV, and we get completely complementary images. Here we get an image or a scan of the sky, X-ray sky, and here we get the comet. So the comet is virtually absent. It doesn't neither absorb nor emit. It's just not there at high energies. And this can be used in order to first detect all these sources and then to remove the areas around these sources in order to minimize the contamination by unrelated point sources. This, of course, has to be, is very important, also done for these maps, because by cutting out these areas, we create artificially insensitive areas for a limited period of time, which would otherwise disturb our photometry. And when this is done, the next thing is to transform all this into the rest frame of the moving comet. I show you this for just this first pointing. We have this big hole. Here you can see how this is now stretched when we transform it into the reference frame of the moving comet. Here for two different instruments. This is for the background map, and this is for this is for one pointing. And if we take all together, then fortunately these holes tend to be washed out, so we get a fairly uniform exposure. So this is now the background map in the coordinate system of the moving comet. The other thing is the exposure map. If we do this, transform this into the reference frame of the moving comet, then we get these images. And here already you see a very important property. If we don't do this, then the full photometry can be easily fooled, because this looks already like a diffuse object which has some extent, but this is just tells us how the sensitivity is distributed over the field of view when it's transformed into the reference frame of the comet. Now, when this is available, when the photons have been transformed, when the background map and the exposure map have been transformed, we can then subtract the background map and divide the rest by the exposure map, through the exposure map, and then we get these photometrically calibrated images. So this is fairly straightforward, this step from here to here. And when this is done, then we can already apply science. A very interesting thing is to deduce, for example, the location of the cometary bow shock just by photometric studies, by studying the morphology of the X-ray emission. For spectroscopy, and this is our main interest here, the requirements are much higher. And therefore I will say a few words about these problems and challenges in generally spectroscopy with X-ray CCDs. This is what we would like to have. So assume this is our CCD, and here it's exposed to cometary X-rays, and then we can analyze the signal. The problem is we have other contributions as well, and they will step by step come up to the bottom. There's a lot of space. So one property of the cometary signal is that it's subject to vignetting by the X-ray telescope. And also, this is important for spectrum analysis, there are two important ingredients which one needs, the so-called RMF. This is the redistribution, which takes into account the modification of the incident signal, spectral signal by the detector, and the ARF, the effective area, which essentially tells us the sensitivity as a function of the energy, which is can be quite variable in case of X-ray detectors. But this is not the only contribution, as I said before. There's another one which comes from the diffuse X-ray sky. We can easily cut out point sources, but we cannot do this for the diffuse X-ray sky. Otherwise, nothing is left, so we have to live with this contribution. This is everywhere, also superimposed on the position where the comet is. And in addition to that, there's an instrumental source of photons, fluorescent X-rays, because the detector, the camera housing, is exposed to radiation, particle radiation, and this particle can cause fluorescent X-rays from the inner region of the detector. So whatever is inside this camera housing, aluminum, silicon, or silicon comes from the CCD itself, titanium, copper, this can produce, in addition, fluorescence lines. And they have a different spatial property distribution. This all is just X-ray photons, but there are also X-ray particles, also particles. This one is obvious. This is the byproduct of this fluorescent X-rays, the photoelectrons. But there are also soft protons. These are the most dangerous things. They have destroyed almost the Chandra ACIS I detector. They don't have the energy to penetrate the housing, but they can be focused, or they can enter the telescope, and because X-ray optics use the principle incidence angle equals exit angle, this also works for soft protons. They are more or less ballistically just reflected by the telescope and guided exactly on a place where we don't want to have them at all. And so they are almost indistinguishable from photons. They have also vignetting, although it's slightly different, but this is a detail. This is something we have to live with. They are also highly variable in time. And then there's a component, minimum ionizing particles. These are the energetic particles which can cause trails in the CCD, like in a cloud chamber. And due to this, they are very easy to spot and to remove. So the MIPS themselves are not a major problem, but the disturbance which they cause in the CCD, which they may cause in the CCD. And I had a very interesting experience when I was working on the first light image of XMM Newton. This is this one, which you may have seen. This is actually what the raw data looked like. And this is full of all these disturbances called by the minimum ionizing particles. There's already an onboard processor which was supposed to remove all them, to exclude them from telemetry, but the particle background was so high that it was only successful to 65%, and this is what remained. So on ground, one can then need to get rid of this rest, which is straightforward, but unfortunately this disturbance, which is caused usually in subsequent frames by these MIPS, is something which one has to live with. And still not the end. This is all external signal. There's also internal signal. The detector itself is producing background by electronic noise, thermal noise, and other components. And this thing is further complicated by the fact that all these instrumental characteristics are smeared along the readout direction by an effect which we call out-of-time event effect. And this is illustrated here. Assume this is your detector, this background, this is your source. The problem is that when the charge is shifted to the readout node, the detector is still sensitive. There's no shutter which would block, otherwise we would not have this problem. Therefore, we get this out-of-time events background, and this is superimposed everywhere along this direction. Fortunately, this is very straightforward to subtract. Here in this example, I show you now background plus this source, 1 second exposure, and now if we had a shutter of 0.2 seconds, we would have this fine image, but we don't have this. So during this 0.2 seconds, we get this smearing of this of both signals. But this already means it tells us what to do. We have to compute this. We have to smear the signal which is inside again, multiply it with the right factor, and then subtract it. And I had originally developed this method for the first light image again. So you see here the original image where bright sources do have this out-of-time events property. And this is then the correction image obtained by smearing the photons randomly along the readout direction. And when this is appropriately scaled and subtracted, then we really can get rid of this effect. Okay, the contributions so far are additive contributions. There's also another thing to consider. Unfortunately, there's in some CCDs the problem that contamination layer is building up. And this is a particular issue at low energies, where we are mainly interested for when we study solar wind charge exchange. And this has another signature. Usually it's a temperature effect, so it's a center-to-edge characteristic. And speaking about sensitivity, there's another effect which is a little bit related to this. This has to do with charge transport. When the charge is transferred from the place where it's located to the readout node, some charge is lost. And this means that the lower energy cut is a function of the distance to the readout node. So if we produce an image in the lowest energy channels, then it's brightest closest to the readout node and gets fainter when we move away from this. And there are some other details like pattern migration for the experts, and which also have to do with this complication with the charge transfer. The spectral resolution also suffers from charge transfer, so the spectral resolution is highest close to the readout node and gets worse away from it. And in some CCDs, in particular in EPIC MOS cameras, the fact that now over 15 years all the sources fall onto the same region in the aim point on the CCD, this has caused some degradation in energy resolution. So we have a spot, unfortunately exactly where normally the objects are placed, which has reduced energy resolution. Now imagine you have an extended source which is moving across this, and you have a nice mixture of all the individual effects, and this does not, it's quite challenging to get rid of this. If you have a point source, that situation is easier, because then you just can take the background very close to the point source, and then when you subtract it, you automatically get rid of all these components. These spatial inhomogeneities are not that pronounced that this is something to worry about. So this is fairly straightforward, but in case of an extended object, this is a real challenge. Another one for comets, which also extended, is to find a region where you can really take the background. This is now a real image. Assume this is a comet, and this is a whole field of view. That's all what you have. Then it's tempting to enhance the contrast and say, okay, this is reasonably dark. These are our areas where we take the background from. But this is not a good idea, because if we had a larger field of view, then we would see that in fact everything is comet emission. So there's no comet-free area, and what we in fact would do in this way is subtract signal from signal, which is not a good idea. It's much better to do a different approach. Rather than subtracting the background, try to model it. So if we have a model for our source, this is now for charge exchange, and for the background, the diffuse X-ray background, we know this from the Rosat-Olskar survey, can be fairly well generally prescribed by a superposition of two black bodies plus a power law. Then we can set up the following equations for the spectral fits. We can say we have a source region and a background region. In the source region is of course dominated by the source, but has also some contribution from background, while background is the opposite. So we just scale these contributions by a constant and couple in this way the fits together. And we can also add some fluorescent emission depending on what is necessary. We are not interested in this, but it is necessary in order to get a reasonable fit. And in addition to that, all these effects which should not be folded through the RMF can be treated in an independent way by detector noise. A detector noise, for example, can be approximated by filter wheel closed data and then appropriately scaled. Again, similar way, you have the same model and you just scale it. And in this way, this has, if it works, it has many advantages. Statistics is straightforward. We don't have problems with negative numbers. All photons are utilized. And we get even, as a bonus, additional information about, for example, the source contribution in the background region. Now, to the spectral resolution, this is a very important restriction for X-ray CCDs. The charge exchange spectrum has too much structure to be uniquely deconvolved by the resolution which is given by an X-ray CCD. We need additional model assumptions. And this here is an interesting example. So this is a real observation, and here is a non-physical model. I have just, for fun, included one line after the other until I got a reasonable fit. The fit actually is quite good, but the model has nothing to do with physics. It's just a description of what we see empirically. By the way, this is the same. This is for people who prefer wavelength and the others who prefer energy. If this plot is perhaps interesting to show you a few of the details of the energy resolution of the detector. If we look at fairly high energies, then we see that line is essentially just broadened. It has a low energy wing. This comes from the fact that the electron cloud is produced very close to the surface, and not all the charge makes it into an X-ray signal. And when we go down in energy, then this component gets progressively brighter and brighter. And here it starts to develop a secondary peak, which here already is brighter than the main peak. So this is from this line. And if you don't know this, then and see this peak here, then you would say there must be emission at this point. But in fact, this is not. There's nothing. This is just the ghost line, which comes from this this point here. And here is even more pronounced. You don't see the main peak at all. You just see the ghost peak. So that it looks like you have an energy shift, which is not true. So this emphasizes why the detector response is so important. It's not just a broadening. It's really a much more complicated function. This is the same for EPIC PN. It's a back illuminated device. The other one was front illuminated. It has in principle the same characteristics, and I think all X-ray CCDs share similar characteristics in this respect. This is again just a toy model, no physics involved, and the same now with a real charge exchange model would look like this. If I blink between those and you just for a moment concentrate on this thick white curve, then you see the fit is quite similar, but the model is completely different. Here's not physical, here's quite physical. This is actually coming from RGS data. I'll come in a moment to that. So this simply means we need a model. We can't do spectral deconvolution without a model, and therefore you are very important. In order to get a solution, Dennis has some time ago put a lot of effort into compiling this list of emission lines and made an interesting approach. He combined lines which belong together into individual groups. So in this way, the number of parameters could be substantially reduced. And these groups were just allowed to be varied as a whole. And in this way, the program became tractable. This is in principle a very nice approach, but it has one disadvantage also mentioned in this paper, the uncertainties of the order of 20%. And this is too much really to justify to fix the individual intensities, because you can't expect that you get a good fit with these uncertainties. So it's really, this is a real problem. In order to be able to understand the X-ray signal, we need to constrain these relative line intensities as good as possible. One way to get around this problem is that we move to devices which have higher spectral energy resolution. For the near future, a lot of hopes are in these microcalorimeters, but they are not yet available. But what we have already available are gratings. And in particular, in XMM Newton, there are two gratings called RGS, reflection grating spectrometers. And they are very, very interesting, very challenging to analyze, but very promising also. One important thing to keep in mind is these are all slitless gratings. This means that when you have an extended source, and this is nicely shown here, this is now Chandra gratings of supernova remnants, and these extended sources emit in particular wavelengths, then you get an image of this source at each particular wavelength. This is very nice as long as the objects stay compact enough that you can separate them. And in the case of Mars, for example, this is possible. And I had applied this technique a while ago. So this is the RGS spectrum of Mars, and you can see that the individual peaks are well separated. And because it's slitless, you can use this in order to accumulate images at the particular energies. And then this is what I have done here for fluorescence, for ionized carbon, ionized oxygen, colored them, and in this way you can, for example, produce a color image from RGS data. This is very nice possibility. Unfortunately for comets, this does not work simply because comets are much more extended. Here this is 30 arc seconds, this is 5 arc minutes. If we scale them approximately to the right solid angle, then you see the problem. So here you have the individual images well separated, but here everything is merged together. Fortunately, there is still a quite pronounced peak at the center, which makes it possible to analyze RGS data. The other problem is that the RGS field of view is much smaller than that of the EPIC CCDs, and therefore there's no way to get background from the same observation. Otherwise, the data reduction works in a very similar way, that one needs to take out the motion of the comet and try to get a tracked image in wavelength space. And this is shown here. So this is the original spectrum in detector coordinates. And when the transformation to the moving object is applied, then we get something like this. So inside this image, there's the comet hidden. In order to get the comet out, this is a standard technique for RGS. The dispersed spectrum is recorded by X-ray CCDs, which have intrinsic energy resolution. So there's a quite good correlation. If you have at a certain dispersion angle a signal, then you can use the intrinsic energy resolution in order to filter out the signal and suppress the background very efficiently. So in fact, this is the area which you are then using. And when this is just used and the rest is ignored, then you get a much better signal and you now start to see structure. And these are in fact little comet images. And fortunately, the comet is so highly peaked that it's not just a structureless feature, but you see individual images, although they are heavily smeared. This is a projection. You see that they have extended wings, but this is not a principal problem. If you know this precisely, then you can do spectral studies. There's still the problem of getting a background, and this is quite tricky. So I had to take it from a different observation, and very useful observations are those of Hubble Deep Field, because for RGS these are empty fields essentially. There's no bright source, and these are long observations, so it gets good statistics. But we cannot use them in this way, because this is not the way we have treated the comet photons when transforming them into the reference frame of the comet. So it's necessary to invent a comet which would have passed through the Hubble Deep Field in the same way as the real comet has passed a different field half a year later. This was the general idea. So it's quite and this situation is even more complicated by the fact that the background was temporally variable. So you have to find a period in this Hubble Deep Field observation where you have a similar signature, temporal signature of the background, and synchronize this with the motion of the comet across the RGS CCDs. So this was a bit tricky, but this was then what I got. And when you then subtract both from each other, you get this image, now individual comet images with very high resolution. The challenge now is to determine the PSF, the response, to know how a comet in one particular line wavelength would look like in this projection. Fortunately, we have 5 instruments in total. There are the EPIC instruments, and then we can use them in order to get this profile, intensity profile, and this can be merged with the intrinsic response of the RGS to get the right response for this comet observation, and then we are able to really do spectral analysis of RGS data. This can be done for various extraction for small region or broad region. Yes, and that's the result. And this is, to my knowledge, the best astrophysical charge exchange spectrum which is available right now. It's full of lines, full of details, in particular in this lower energy range. So this is the model, and this is the convolved model. It's the residuals, which works quite well. And with this one can answer interesting questions. For example, this famous G ratio. This can be directly deduced from the relative intensities from this spectrum. There were various predictions in the literature. Perhaps it is not, the literature scan is quite old. Maybe there are newer ones. And here we can directly determine this G factor to be 3.7 plus minus 0.5, so even with quite good statistics. This shows what can be done with such spectra. Some other possibilities are we can, for example, determine this line ratio 5:1 to 2:1 and get this value which is approximately consistent with expectations. In another case, we have just an upper limit where some theories predict that we should have seen a clear signal. So this is stuff. These are not the final results, but it shows you what can be done with such spectra. You may have seen here that I have here combined RGS spectra with another spectrum. This is from EPIC PN. And now comes the problem. If we look carefully at this, then we see that they don't match perfectly. Match could be better. And this brings me now to the last part, the instrumental calibration. This is a very, very important topic. And in fact, this is not related to COMET, not related to XM Newton. It's a general problem. And there's actually a group, it was formed a few years ago, where all experts from the various high-energy satellites come together. They will meet next week in China. They have annual meetings. And they have established reference sources. And the one which is of most interest for us is this one. This is a supernova remnant in the Small Magellanic Cloud, which has a very rich spectrum. This is an RGS spectrum of this remnant, not too different from a comet spectrum. And here, this has been observed with various instruments. And the punchline of this is, here I plot the plus minus 20% deviations in intensity between the model and the observations. And in many cases, the deviations, you find areas where you have deviations of this order. So this is really a problem to get good, well-calibrated data, good calibration at this energy range. And I'm mainly personally responsible for this one, the EPIC-PN camera. And here we had for a long time to do with a very nasty feature here at low energies, which simply did not fit. And the problem was that the response matrix was calculated with a semi-physical model, which did not have enough flexibility to be tuned to reality, so to speak. And in the case of calibration of another, or preparation of the calibration of another instrument, EOSITA, where my institute is working now heavily, I have developed a different approach, which is not based on physics, but it's purely a mathematical description of the data. So this is, for example, the response, the signal you get when you have an incident X-ray of 2.3 keV. And then you get this quite complicated shape. And I have here then assigned various shaping parameters and have tried to characterize their dependence on the energy so that I'm able to tweak them if needed. And this worked surprisingly well. And here I'm happy to show you now, this is a result just a few weeks old. This is a situation essentially for the first 15 years of XM Newton, and now you will see how this improves. This is now a fit where the RMF is fit. This is a very sophisticated thing, not a spectrum, not a model, but the whole matrix. And in this way, we can almost halve the residuals. There's still something left, but with this technique, I think we have now a very powerful tool to attack this problem. And this was one of the main showstoppers for publishing cometary spectra, because you could either publish the RGS spectrum or the EPIC-PN spectrum, but they would not agree with it. Otherwise, this is not a nice property. Now I hope this can be fixed, and we can then now finally combine the spectra of the individual instruments. And this can be done in principle in the same way as showed before. So this is what I had shown you a little bit earlier, where we have this modeling of the background, the source, the photons, and the detector. And we can do in principle the same for the other four instruments. And the general idea is that we then couple the fluxes, the overall fluxes of the individual instruments to allow for slight calibration uncertainties, and do everything in a combined fit. So this is a quite sophisticated thing. I cannot do this yet because I don't have the final RMF values at hand yet, but I have already tried whether formally this works, and it does. So this is not just fiction, this really works. This is now a result from a combined fit, where I show you now here just the PN results, the source region, the background region. This is the incident charge exchange spectrum superimposed on diffuse X-ray sky. This is the same result for MOS1, source region, background region, and for MOS2. And by the way, you see that you have really everywhere comet. There's no comet-free region. And this is for RGS, all the same fit. So this is the summary of all the... So we have 10 spectra which have to be fit simultaneously. And the big question is now what to do with the line ratios. If we allow them all to vary freely, then we cannot determine them. We have too many free parameters. if we fix them, then this is too rigid. We have to really to rely that all the line intensities are really accurate. This is not the case. So what I have now started to implement is some hybrid technique. I have put the predicted preferred line intensities as fixed parameters into the spectrum and have allowed each relative line ratio to change here between 50% and 200%. So it could be half or double the value. But in order to motivate the fit to be close to the predicted or preferred case, I have quadratically added a penalty function to the chi-square, so that if the results are similar for similar combinations of line intensities, the one which is closer to the prediction is preferred. This works in principle quite well. So in all these cases it worked. Here we have but one case, but this is just an example. This is not taken seriously, where one line, the fit would like to increase the relative line strength by more than a factor of 2. The problem is how to scale this about variability to allow, and I think this is now the real why I'm so appreciate it so much to be here. Perhaps I can get feedback what you think is a good approach. Technically, this is now, I think, all possible. The question is now to have a reasonable input for such a spectral fit. Okay, I think my time is over.
Question for Konrad. Brett, are the XMM representatives to the ITAMP meeting or your results talked to them hopefully regarding the response matrix?
Well, we had an internal EPICAL meeting last week in Spain, but unfortunately two people who attended there will be at the IRCheck meeting, so I think this will be propagated. Although this is, I have to emphasize, is result. Just let it run over Easter. This is very fresh, and one has really to put in more effort in. But I'm very optimistic now. This is a right approach. Could also be applied to other instruments in principle.
I have a question about this forbidden resonance transition and intercombination. Because you show some different numbers here for ratio.
Yeah.
And these numbers, they are something depend on the target. For example, Alex and me present this for hydrogen for Mars. Yeah.
Mm-hmm.
Assuming the target single atom, a single electron atom. Yeah. Dennis case for comet, probably it is water. Yeah.
Yeah.
Is it possible to look on the remote sources? I talk about stable remote sources, like the supernova and something, and to re-establish this ratio.
Well, to my knowledge, I think we have heard this yesterday. Supernova remnants, you have a superposition of various components, and therefore, I think it's not easy to extract a clean charge exchange signature from these ratios. You can determine the ratios, but then the interpretation is.
The mixture of the thermal mechanism. But do we have point sources with clean charge transfer?
I'm afraid.
Except Mars, your famous Mars.
No, even Mars is contaminated in this respect by fluorescence. Yeah. It's difficult.
Along these lines, the approach you showed for the one measurement was for one particular comet.
Right. Yeah.
It looked like it was a pretty trivial procedure. I'm sure you can do that in like half an hour with all the steps that you laid out. But be realistic. How many more comets are there with good data that you could apply this technique to? How many graduate students needed to?
Well, this one was admittedly one of the best cases. I think we may have a few of this quality, and for the others, it's already questionable whether RGS is sufficient to apply this technique. So my general idea is to use this one as a test and training set, and then to try to proceed to the fainter ones.
Are all these problems that you had to account for in modeling this, are they going to be present in the Astro H observatory, and if they have to be accounted for?
Well, microcalorimeters work in a different way, and I have to admit I'm not familiar with the details.
Well, most of those things would be the same for common observation, except you only have a 5 arc minute field of view, so
But his comment, I think your idea is really good because there's multiple targets for water with the CO2. There's some variation in the line ratios with velocity.
Uh-huh.
So, and I'm sure the 90 is well known for water. The line ratios are.
Okay, well, there's also the additional complication that along the line of sight, we have different velocities, probably with different components. So in principle, we would also need a model for the comet, interaction of the solar wind with the comet, implemented in addition to the line ratios.